5.4b, example 1. We want to solve the equation 2 cosine x plus sine 2x equals 0. When solving an equation with a trig function, we always want to have the same angles. In this case, one of the angles is x and the other is 2x. We need all of the angles to be either x or 2x. Sine of 2x is a double angle formula. We can replace sine of 2x with 2 sine x cosine x. Notice all of the angles are now plane x. Sometimes it's a good idea to make all of the trig functions in the equation the same. For example, all sine or all cosine. It is okay for there to be different trig functions as long as when you get everything to one side set to 0, that the expression will factor. Both terms have a 2 and a cosine x in common, so we can factor 2 cosine x out. With our equation factored, we can set each piece equal to 0. Solving the equation on the left, we divide both sides by 2. Cosine of x equals 0. To find the answer to cosine of x equals 0, we are thinking of the angles on the unit circle where the x-coordinate is 0. This occurs at pi over 2 and 3 pi over 2. Solving the equation on the right, we subtract 1 from both sides. The sine of x is equal to -1. To find the answer to sine of x equals -1, we go to the unit circle and find the angle measures where the y-coordinate is -1. This only happens at angle measure 3 pi over 2. The solutions to this equation are pi over 2 and 3 pi over 2. If we want to check our answer, we can graph the equation. X-intercepts are the solutions to the equation. Notice I have only graphed from 0 to 2 pi. We only have 2 x-intercepts from 0 to 2 pi. The first x-intercept, if I were to use the 0 feature of a graphing calculator, is 1.571. If I divide pi by 2, I will get 1.571, verifying that pi over 2 is a solution. The second x-intercept is 4.712. 3 pi over 2 is equivalent to 4.712, verifying that 3 pi over 2 is a solution. When solving this equation, we only looked for solutions from 0 to 2 pi. But if we want to solve this equation and leave out on the interval 0 to 2 pi, we will have an infinite number of solutions. Graphing 2 cosine x plus sine 2x over a larger interval than 0 to 2 pi, we get this graph. I graphed from -8 pi to 8 pi. Notice there are quite a few x-intercepts. All of these x-intercepts are solutions to the equation. The first two to the right of the y-axis are the two that we found when we only looked at solutions from 0 to 2 pi. Notice if I start with pi over 2 and add 2 pi, I get to an x-intercept, which is 5 pi over 2. If I add 2 pi again, I will get to another x-intercept, which happens to be 9 pi over 2. I could continue doing this forever, moving to the right to find the next x-intercept or the next solution to the equation. I could also start at pi over 2 and subtract 2 pi, arriving at an x-intercept, and continue subtracting 2 pi forever, continuing to get additional answers to the equation. If we want to write a solution that includes all of these answers, we might start with x equals pi over 2. Realizing that we want to add and subtract 2 pi as many times as we want to make the solution generic, we will add 2 pi k. We don't need to say plus or minus because we are going to let k be an element of the integers. Integers are numbers 0, 1, 2, 3, 4, etc., and negative 1, negative 2, negative 3, negative 4, etc. If I were to substitute 0 in for k, we would have pi over 2 plus 2 times pi times 0, which would give us our first solution, pi over 2. If I let k equal 1, then we would get 5 pi over 2. If I let k equal 2, I would get 9 pi over 2, and so on. If I let k equal negative 1, I would get negative 3 pi over 2. If I let k equal negative 2, I would get negative 7 pi over 2, etc. Now let's take a look at our other solution on the interval 0 to 2 pi. 3 pi over 2 was one of the x-intercepts. And just like the other one, if we were to add 2 pi repeatedly, we would continue to get other x-intercepts. If we go back to 3 pi over 2, we could subtract 2 pi as many times as we wanted and continue to get even more x-intercepts. Every x-intercept is a solution to the equation. To write the generic solution that is generated by 3 pi over 2, we would let x equal 3 pi over 2, but add 2 pi k such that k is an element of the integers. This is usually sufficient. This would be our final answer. However, like most things in math, if we can simplify, we should. Sometimes you see a solution in the back of the book that doesn't look like yours, even though you feel fairly certain that what you've done is correct. Let's look at the pattern of all of the x-intercepts. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. Notice those are only 1 pi apart. To get from pi over 2 to the next one, we would just add pi. If we started at pi over 2, we could also subtract 1 pi repeatedly to get from one x-intercept to the next. So we can merge the two equations we wrote, pi over 2 plus 2 pi k and 3 pi over 2 plus 2 pi k. We can say x equals pi over 2 plus pi k, such that k is an element of the integers. If you want to solve an equation for all solutions, and the equation you are solving contains sine, cosine, secant, or cosecant, you want to add 2 pi k such that k is an element of the integers. That is because answers for those trig functions repeat every revolution, every 2 pi. If you were solving an equation that contained tangent or cotangent, you would want to generically add plus 1 pi k such that k is an element of the integers. This is because tangent and cotangent repeat answers every 1 pi. Usually, when you solve one of these equations, you will use all of the little equations that you create. This is an example of when you can merge 2 equations. Something else to be on the lookout for, if you don't match the back of the book, is one of the equations that you created might generate duplicates. So then you end up throwing out the one that's generating duplicates.